Hello, welcome back to the channel. So let's move on to a new concept which is about partial fractions. So whenever you have your factored expressions in your denominator of the integral expressions or some quadratic expressions which cannot be simplified further, you will most likely use a new concept which is known as the partial fractions. So what we do in these cases is when we have factored out terms in our denominator, we usually break those terms into different components such that we know the integral of those individual components. For example, let's take this basic example over here. Let's suppose in your indefinite integral you have a px plus q term in the numerator. You can take p and q to be any real values, but in the denominator you have a factored out term which looks somewhat like x minus a, x minus b. So you can write this term as simply capital A upon x minus a. So you can break this term into two components, which would be capital A upon x minus a plus capital B upon x minus b. And then when you'll equate both of these equations, you can solve for your capital A and capital B, which would be constants in this case. So that is the basic idea about partial fractions, that whenever we have these type of expressions of these forms, we usually break those expressions into multiple components such that we know the integral of all those multiple components rather than solving the whole indefinite integral in this case. So for example, when we will break this integral, when we'll break this expression into two parts, we can clearly see in this case that we know the integral for 1 upon x minus a, which is ln x minus a, right? And we also know the integral for 1 upon x minus b, which would be ln x minus b in this case, right? So the calculation of indefinite integral or definite integral as well becomes much more simple when you have your expressions of this form rather than your expressions of this form, right? So this is the basic idea of partial fractions, and you can extend this property to different types of other expressions. For example, you have another expression which is you have a px plus q term in the numerator and you have an x minus a whole square term in the denominator. It can be easily simplified to a upon x minus a plus b upon x minus a to the whole square. So again, you see a different pattern over here. If you have an x minus a whole square term, you have a squared factored term. So what you'll do is you'll take the term first and put that in the denominator such that you have an a upon x minus a term, and then you'll take the square of your factored term and do the same thing with another constant. And then you have multiple cases over here. You can see that you have x minus a, x minus b, x minus c, which can be easily broken down into three parts. The same property that we used in the first rational function case. And then in the fourth one, we have a combination of both of those patterns, the patterns which we saw in the first and second expression. So what you'll do is first you'll write a upon x minus a, then you'll take the square of this x minus a term, you'll write b upon x minus a whole square, and then you have one x minus b term, so you'll write c upon x minus b. And now at last this is a different expression. So in this case, whenever you have a quadratic equation in the denominator which cannot be further simplified, which cannot be further reduced, or cannot be further factored, you'll do the same thing for x minus a case. You know that whenever you have an x minus a term in the denominator, you do capital A upon x minus a. But for the quadratic expression which cannot be factorized further, what you will do is you'll take that quadratic expression in the denominator and then you'll take the polynomial of 1 degree lesser than the quadratic polynomial in this case. So since in this case the polynomial is of degree 2, you have an x square term, so it's of degree 2. So in the numerator you'll take a polynomial of degree 1. I hope that makes sense. Don't worry, we'll do a couple more problems based on these concepts and we'll see this process in detail, how we break down our rational functions of this form, our indefinite integral expressions of this form, to these expressions and calculate them easily using partial fractions. So that's it for this video. In the next video, we'll use partial fractions to divide an expression, a complex expression, into different multiple components by only using partial fractions in that case. So feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.